According to the National Electrical Code, a grounding conductor is required to be run with the medium voltage cable from the top of the pole to the disconnector and then to the transformer. NEC Article 250.180 states where high voltage systems are grounded, they shall comply with all applicable provisions of the preceding sections of this article and with 250.182 through 250.190, which supplement and modify the preceding section. This means that since the utility system at the service point is grounded, the customer-owned primary system must also be grounded in accordance with Articles 250.182 through 250.190. NEC Article 250.188 states that grounded high-voltage systems shall have an equipment grounding conductor. The equipment grounding conductor shall be run with the circuit conductors in the same raceway, cable, or cord. Therefore, a grounding conductor must be run with the medium voltage cable from the top of the pole to the disconnect and then to the transformer. The customer cannot elect to supply the premises with an ungrounded system because the utility system is grounded at the service point. It is important to understand the code requirements for high voltage systems. Grounding ensures safety and proper operation of electrical equipment. The requirements of NEC Article 250 are designed to protect people and equipment from electrical hazards. When dealing with high-voltage systems, it is crucial to adhere to the code to prevent potential risks. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Without proper grounding, fault currents can take unintended paths, leading to equipment damage, fire hazards, and electrical shock. Understanding the relationship between the utility system grounding and the customer-owned system grounding is essential. Since the utility system is grounded at the service point, the customer's system must also be grounded to maintain a consistent grounding reference. This ensures that fault currents can flow effectively and that protected devices can operate as intended. The equipment grounding conductor plays a vital role in providing a low impedance path for fault current. It connects the non-current carrying metal parts of electrical equipment to the grounding electrode system. This connection helps to minimize the voltage potential between these metal parts and ground, reducing the risk of electric shock. Running the equipment grounding conductor with the circuit conductors in the same raceway, cable, or cord ensures that the impedance of the grounding path is minimized. This is important because a high impedance grounding path can limit the flow of fault current, preventing protective devices from operating quickly and effectively. The code requirements for grounding high voltage systems are not optional. They are mandatory to ensure the safety of people and equipment. Ignoring these requirements can have serious consequences. Firstly, a proper grounding system is essential for personnel safety. By providing a low impedance path to ground, fault currents are safely conducted back to the source, tripping circuit breakers or fuses and preventing dangerous voltage levels from appearing on equipment enclosures. Secondly, equipment protection is greatly enhanced. Grounding helps to limit voltage surges caused by lightning or switching operations, protecting sensitive electronic equipment from damage. A well-designed grounding system also minimizes the risk of fire by quickly clearing ground faults. Thirdly, compliance with electrical codes is paramount. The NEC, specifically Article 250, outlines detailed requirements for grounding and bonding. Adhering to these regulations ensures that electrical installations meet accepted safety standards and are less likely to pose hazards. Fourthly, system reliability is improved through effective grounding. A stable ground reference minimizes electrical noise and interference, leading to more consistent and reliable operation of equipment. This is particularly important in sensitive electronic systems. When designing and installing a grounding system, several factors need consideration. 1. The size of the grounding conductor must be adequate to handle the maximum potential fault current. The NEC provides tables to determine the appropriate size based on the size of the ungrounded conductors. 2. The grounding electrode system should provide a low resistance connection to the earth. This typically involves using ground rods, ground plates, or underground metallic water pipes as grounding electrodes. 3. All metallic enclosures, raceways, and equipment frames must be properly bonded together and connected to the grounding electrode system. This ensures that all non-current carrying metal parts are at the same potential, minimizing the risk of electric shock. 4. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Ground connections should be checked for corrosion and tightness, and grounding electrodes should be tested to verify their resistance to ground. In the specific scenario of a 13,200 volt 3-phase 4-wire system supplied by the utility company, the requirement to run a grounding conductor with the medium voltage cable from the top of the pole to the disconnect and then to the transformer is clear. The utility system's grounded nature at the service point mandates that the customer-owned primary system also be grounded. This is further reinforced by NEC Article 250.188a, which explicitly states that grounded high-voltage systems shall have an equipment grounding conductor run with the circuit conductors. Therefore, the contractor does not have the option to elect to supply the premises with an ungrounded system in this case. The grounding conductor must be installed to ensure compliance with the NEC and to provide a safe and reliable electrical system. The size of the grounding conductor must be determined based on the size of the ungrounded conductors, as specified in the NEC. The grounding conductor should be installed in the same raceway cable or cord as the ungrounded conductors to minimize impedance. The grounding conductor must be connected to the grounding electrode system at the transformer. The grounding electrode system should consist of ground rods, ground plates, or an underground metallic water pipe. All metallic enclosures, raceways, and equipment frames must be properly bonded together and connected to the grounding electrode system. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. It is crucial to consult with a qualified electrical engineer or electrician to ensure that the grounding system is designed and installed in accordance with the NEC and other applicable codes and standards. Ignoring these requirements can have serious consequences, including electrical shock, equipment damage, and fire. Grounding is a critical aspect of electrical safety and should not be taken lightly. In summary, when a utility system supplies a grounded system at the service point, the customer-owned high-voltage system must also be grounded in accordance with the NEC. This requires running an equipment grounding conductor with the circuit conductors in the same raceway, cable, or cord. The equipment grounding conductor must be connected to the grounding electrode system, which provides a low impedance path for fault current to flow back to the source. This ensures that protective devices can operate effectively and that the risk of electrical shock is minimized. Adhering to these grounding requirements is essential for the safety of people and equipment. It is important to understand the specific requirements of the NEC and to consult with a qualified electrical professional to ensure that the grounding system is properly designed and installed. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is updated every 3 years to reflect changes in technology and best practices. Article 250 of the NEC is dedicated to grounding and bonding. It provides detailed requirements for grounding electrical systems and equipment to ensure safety and prevent electrical shock. Grounding is the process of connecting electrical equipment and systems to the earth. This provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding is the process of connecting all non-current carrying metal parts of electrical equipment and systems together. This ensures that all metal parts are at the same potential, minimizing the risk of electric shock. The NEC requires that all electrical systems be grounded, with some exceptions. The grounding requirements vary depending on the voltage of the system and the type of equipment being used. For example, systems operating at less than 50 volts may not be required to be grounded, while systems operating at more than 1000 volts have more stringent grounding requirements. The NEC also specifies the types of grounding electrodes that can be used. Grounding electrodes are conductive objects that are buried in the earth to provide a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The NEC also requires that grounding electrodes be installed in a specific manner. For example, ground rods must be driven at least 8 feet into the ground and must be spaced at least 6 feet apart. The NEC also provides requirements for the size of grounding conductors. Grounding conductors are used to connect electrical equipment and systems to the grounding electrode. The size of the grounding conductor must be adequate to carry the maximum potential fault current. The NEC provides tables to determine the appropriate size of grounding conductors based on the size of the ungrounded conductors. In addition to the general grounding requirements, the NEC also provides specific requirements for grounding different types of equipment. For example, there are specific requirements for grounding transformers, generators, motors, and appliances. It is important to consult the NEC to determine the specific grounding requirements for the equipment being used. Grounding is a critical aspect of electrical safety. It is essential to follow the NEC requirements to ensure that electrical systems are properly grounded and that the risk of electrical shock is minimized. Consulting with a qualified electrical engineer or electrician is recommended to ensure that the grounding system is designed and installed in accordance with the NEC and other applicable codes and standards. Proper grounding not only protects people from electrical shock, but also helps to protect equipment from damage caused by voltage surges and other electrical disturbances. A well-designed and properly installed grounding system can also improve the reliability and performance of electrical equipment. Therefore, it is important to pay close attention to the grounding requirements in the NEC and to ensure that all electrical systems are properly grounded.